earlier we find out that how these output devices, basic simple output devices, are connected to microcontroller, and next step is that we try to connect some input devices to our processor. And simplest input device is the switch, and more general or more complicated switches are keyboards. So next we will connect the 4x4 keyboard to our microcontroller and use that as an input device. Here's our practical implementation. So we will have this small 16 button keyboard here, and we will connect that to our microcontrollers in that way that we can read the keyboard statuses. We read the statuses of these buttons here. Let's first look back a little bit how our input devices are working. So here, if this is means the keyboard buttons here, so when I press this button, it closes the 5 volt voltage to the signal line, and then we have to read the signal line level here to our CPU. And here was that electronic switch that we were studied more detail in earlier sections, but here's still the brief simple principle picture how these input devices are working. So if we would like to read the status of the switch, we have to switch on the electronic switch here for a very short period, which is controlled by control bus here from CPU, and when these switches here are closed, then the signal could go through the switch to data bus, and the CPU can then read the statuses which are in the left side of these input circuits. And as many input circuits we need more control lines to activate each of these circuits, and then we can connect parallel as many input circuits, input switches as we would need to do. But here's the basic idea related for the earlier presentations, how these input systems are working. What is the idea of these simple input devices? And here's the real circuit from this AVR processor. That was that output part of this I/O port, and here's the input part of the I/O port. So here is this 3-state buffer here. You could, if you simplify, you could think that the signal goes from this input pin through this sleep circuit, through these latches here to here, and here's that 3-state buffer or that electronic switch which will left the input signal to data bus for a very short period when the CPU is reading that, and in other times this 3-state buffer is disabled and not let any signal go through to that buffer. And here's this clock signals. These are used to synchronize these latches here. This has not much minimal functionality for the basic idea. This is only for the synchronize the input signals to the same time base. And here's this sleep circuit is used to put the processor in such state in sleep mode that it doesn't take any current. It doesn't drain any current from the batteries. But here's the pins. If it configured input, the signal goes from here through this circuit to here, and then this 3-state buffer left the signal to data bus, and then the CPU can read the status of the input pin. And of course then this output 3-state buffer is disabled when the pin is used as an input pin. So in the next exercise we will connect this 16-button keyboard to our C port. Here's the basic idea how this keyboard has been wired. So there are, as I said, there are 4x4 keyboard. It means that there are 4 lines, horizontal lines, and then these vertical lines are here. There are 4x4. And how this keyboard is working, in each of these keys could be represented by a switch. So for example, if I press key 1, it short circuit this line and this line. So then if you put ohm meter here between this line and press the number 1, it should show very low resistance. And if you measure the resistance against the other lines, they should be that should be quite high, maximum display of no resistance at all. And if I press this A button, then this line and this line will be short circuit. So you could think that there are 16 switches inside the keyboard. That's the idea how the keyboard is working. But of course there are only 8 lines here, so there's no individual lines from each keyboard, but these keyboards are in matrix configuration, so there are 4x4 lines. But in the first exercise we will use only these 4 keys from one line. So there's one common line here, and then these individual key lines here. This is part of this. This is the part picture of this big keyboard picture. And here's the schematic diagram of that our keyboard wiring or our keyboard connection. So here are these switches, keys from that upper line 1, 2, 3 and A. These are these keys which represents those switches here. And that switch 1, which means number 1, is wired to C port 0 bit, and number 2 for C1, C2 and C3. And the common line here is grounded, so it will be connected to ground. And so here is the representation of that. So these are the numbers, and here are the C port equivalent bits. So that's the idea how the connection, how the wiring is done in the circuit diagram level. Here's bigger picture of the wiring. So this key 1 goes to Z0, number 2 goes to C1, and so on. And that common line here is the upper horizontal line, so that goes to ground. So it means that if I press 1, then this Z0 bit is connected together to ground, and if I press C1, that is connected to ground, and so on. So what we have to do next is that as we are using a C port and the keyboard is the input device, so we have to configure the C port as an input port. Earlier we configured our D port as an output port, as we were using these output devices, but now we are using input devices, and then it usually means that this port will be configured as its input ports. And here's the table which shows that what kind of possibilities we will have for the configuration of this each individual I/O pins. And here's this data direction register. It's the same data direction register that we were using in our output exercise, but now we are putting the data direction register bits to input bits. So it means that if we put the equivalent bit to 0, then it means that this pin is an input pin. Here 0, and the meaning of that is that the pin is input pin. And there are two, as you can see, here are three input mode possibilities. And what is the difference between these statuses? That it's possibility to switch on so-called pull-up resistor. The pull-up resistor is a weak resistor that connects the input pin to +5 volts. So it means that the input pin is not floating in that kind of situation. There is a weak connection to +5 volts. So then, if there are no external connection to the pin, it will remain in +5 volt, which equals logical status 1. Here's the idea of this pull-up resistor. This is the I/O pin, as we have been configured as an input pin, and here's the pull-up resistor. When we switch on, activate this FET switch here, then it means that this is the +5 volts. So it means that in this side of this resistor there's +5 volts connection. And of course it means then that if there is no other external device driving this pin, this resistor pulls the voltage to +5 volt, and then it means the logical status of this pin is then logical 1. And if there are some external device which is grounding this pin, then of course the status is 0. But as this is a very weak resistor, there won't be any short circuit or not too high currents even when the pin is grounded. But when there is no connection, the pin is in defined state, which is that logical 1. How to activate that pull-up resistor? Let's see that. So we can activate the pull-up resistor by writing logical 1s to input port. That was the output port. If we write 0 to output port, then the output will be low. Logical 1, then the output will be high. But in the input port, it's not usually that we are not writing anything to input port, but in this case, that if we would activate the pull-up resistors, we are writing 1 to input port, and then that will switch on these pull-up resistors. Of course, the output we can drive the output, but only what we can do in the input. Writing to input port is that we can switch on or switch off the pull-up resistors. And here's the example how to control this data direction register. It's the same like way as earlier, so we will write DDRC as 0, 0, 0, 0. So it means that all these 8 bits are 0, then it means that whole port C is an input port. All pins are input pins. And if you would like to activate 4 lowest bits as pull-up resistor switch off, then we will write to input port. This in here we were defining the C port as input port, but if we write to that port 4 lowest bits as ones, it means that for C0 to C3 bits the pull-up resistors are switched on. And here again a picture of these data sheets, this hardware processor data sheets, and here are these data direction register C, and here's the register description of that. By writing zeros here, we define that port to be input, and we could, for each individual pin, we can decide is that input or output. And the same kind of functionality is the same kind of idea is for all the other ports also, C, D, A and B ports. Only the data direction and then the letter after that defines that which port we are trying to influate. Okay, earlier we defined our port to be as an input port, and then the question is how to read the input statuses from the input pins. In our processor we will have this pin C port. That means that this is the register that where we could read the input pin statuses. And how to use that is that, for example, if we have a variable myvar and we would write code line myvar equal pin C. That means that the port C pin statuses are read to variable myvar. So port C is an 8-bit port, so there are 8 pins in that port, and as this is a type of byte, this variable, so then in each of these bits in that variable is the equal status of the input pin. Here is the basic idea what you should do if you would like to read for those 4 buttons that we were connected to our C port. First we have to define the C port pins as an input. In this case at least those 4 pins where the buttons are connected, the switches keys are connected, define those pins as an input, and then switch on the pull-up resistors. So that means that these pins are then in defined state if there are no key and not any key pressed. And then you could make a loop or put the code to loop side. You can read the key statuses through this C port by reading this pin C register to variable, and then because we are using only 4 lowest bit that we are needed, then we can remove the status of the upper bits because we are not using those, and those might mix our code, and that we can do with this AND operator. So if we AND our variable with the 0x0f, it means that after that there are left only statuses of those 4 lowest bit of bin C register. And then if we would like to check that, for example, we could use the if statement that check that if the key 1 pressed, here was our circuit diagram. So if we press this key 1, switch 1 here, then this C0 will be 0 voltage, logical 0. And if we press this number 2, then Z1 will be 0. And if no keys are pressed, then the status is logical 1. If you press some key, it goes to 0, otherwise they are in logical 1. So here with the if statement we could check that as we were masking here highest bits to be 0, so that we know that the 4 highest bits are 0, and if the key bottom 1 is pressed, then the lowest bit is 0, and the other keys they are not pressed, so then they are logical 1. So then we know that if our bit combination is this one here, we know that key 1 has been pressed. If key 2 has been pressed, then this bit here is 0 and the other bits are 1. So that's the idea how we can check that which key has been pressed. We have to check that if the key is pressed. For example here, if as with the if statement. So here again, define the data direction register so that the C port is the input port. Then switch on the pull-up resistors for needed pins, needed lines. Then we can read the C port pin statuses to some variable, for example here at myvar, and then mask not needed bits away and left the needed or used bit to stay in the variable. And then with the if the statement we could check that if that certain key pressed or not. Okay, now it's your time. Try to create a program that prints the pressed key to 7 segment. The 7 segment should be working as you have tried that already. So now your task is to create a program that detects the pressed key and prints the key number to 7 segment. Exercise 8. If you didn't do the function in earlier exercise, now it's time to do function that reads the pressed key. And the function should return numeric value for that equals the pressed key. So if I press key 1, the function returns the numeric value number 1 and 3, 3 and so on. As this A is a hexadecimal number, usually it equals 10. So that's the numbers that the key should return. And the function should wait until the key has been pressed. So when you lift off the key, not pressing anymore, then the function should return, not before that. And probably you don't know, but in these kind of keyboards there is so-called key vibration. It means that if there's very fast program software, it could detect the key vibration if the software is too quick. The key vibration means that the status of the readed key is vibrating for the short period from 1 to 0, 0 to 1. So you have to wait, let's say 15 milliseconds before you know that the key vibration is done. You could notice that your program seems to be crazy if it's not working in the feasible way. If you are not trying to prevent for the key vibration. Usually you can do that in that way that you put only short delay to your detection when you detect the keys, so the delay will handle usually the case. And of course then test the functionality of your program that it really works, but you can use that 7 segment to output the numbers. Exercise 9. In earlier, if you didn't use the loop statement to detect different keys, buttons, now it's time to create some for loop statement based program that will detect the pressed key. So idea is that first check the key 1, key 2, key 3 and key A. And as you noticed here, what is happening here is that the bit here, the 0 is shifted in each round 1 time left, left, left. And that you can do with the for loop. Create some, for example, the mask variable here, where you put the lowest bit to 0, and then here we are shifting left those bits in that variable. So first it's here, then it goes to left, left, left. And each of these statuses, each of these rounds here, we could check that if that key pressed, this will test number 1, number 2, number 3 and A. So with this for loop we can test if the loop goes from 0 to 3, it goes 4 rounds, and as we will have 4 buttons, 4 keys in our keyboard, we could test those keys with this for loop. Here's exercise 10. Now let's do some small user interface, simple user interface. So in this exercise, first you have to print number 5 to 7 segment, and then if we press number 3, the value in the 7 segment will be incremented by 1, and if we press number 1, it will be decremented by 1. So with these buttons 3 and 1, we can increase the number or decrease the number in the display. And if we are pressing A, the number goes back to 5, and if we try to go over our display resolution, which is F, hexadecimal F equals 15, then we start again with a 0. And in other direction, after F, we come back to 0. And now it's time to use for whole 16 buttons, whole 16 button keyboard. And it will be done in that way that this C port keys remains as they were earlier, connected to C port, And then these horizontal lines. Earlier only one horizontal line was used and that was grounded, but now we will connect these horizontal lines, horizontal wires to our P port. And here are these P-port indexes and the nano circuit board layout indexes. And here's exercise 11. You could ask if you feel that this is too complicated or too difficult, you could also ask help from the assistant from your teacher. But let's go through this basic idea how this should work. The idea is to read all these 16 buttons, and here are some tips how you could do that. It's feasible to keep the C port connected as earlier, as you were reading the one horizontal line. And now we are using this P port as output port, and the horizontal lines was connected to P port. And how that helps us. In earlier we were grounded that one horizontal line, but how to do that grounding in more feasible way? We can use this P port to grounding these horizontal lines. In this exercise we were grounded this upper horizontal line here to ground, but now we have been connected all these horizontal lines to P port. So what we can do now is that we can control the P port in that way that we will put this line, for example, to 0, and if these lines here are logical 1, then it equals this kind of situation. This one line is grounded and the other horizontal lines are in logical 1. So here. So these lines, these red lines, are now controlled by P port. So what we can do, in the first internal loop statement we are reading, is this key pressed, this key pressed, this key pressed, or this key pressed from that upper line, upper row line. Then we will, after that, if no keys has been pressed, then we can control from adjust from the control that from the P port that this line will be 0, this line will be logical 1, this will be 0, and these are logical 1s. So then we can, in the same way, we can go through this horizontal line, check which is there any key pressed. If not, then goes to next line and next line. So then what we have to do is that we are going through these buttons 4 times 4. First these columns here, from left to right or right to left, doesn't matter, and check that if any key is pressed. If no key is pressed in the upper line, then we can go to next line and do the same routine. So you have to do the routine 4 times 4 times, then you have been checking all these 16 keys. It's basically the idea is quite simple, but the difficulty is of course to generate the real functioning software. You could also ask some reference program from your teacher if it's too complicated to you. And that was all from these keyboards. And in the next section we go to connect the LCD display to our module.